So the unit we had before this was all about quadrilaterals and other polygons. So it was 4-sided figures and 9-sided figures, all that good stuff. Well, now we're going to jump into circles. Circles is our next unit, unit 10. So first things first, what is a circle? Great question. So glad you asked. I know you know the shape, but do we know the actual definition for that shape? A circle geometrically is defined to be a closed figure formed by a set of points that are equidistant to a given point named the center. So if we think about an actual circle, and you have one here, all of these points along the edge of the circle are equidistant or the same distance from the center A. That's the definition of a circle. I know you know what a circle is, but geometrically it is the set of points all equidistant from the center. So they're all the same distance away from center A. So, circles have a ton of vocabulary. So the first vocabulary word for today is the radius. I think you know what this is. Can someone tell me what a radius is? Amazing. Halfway across the circle. So if I were going to highlight the radius in this image, there's a bunch of options for the radius. The one I want us to highlight is this. Oh, I didn't change the highlighter. Is this right here. This is the radius of the circle. It is the distance that all of those points that create the circle are away from the center of the circle. That's the radius. I'm using red for radius today. The next vocabulary word is diameter. I think we know this one as well. What is a diameter of a circle? Yeah, like the full length all the way across the circle. So definition-wise, it says a segment that crossed through the center and has 2 endpoints on the circle. It bisects the circle, cuts it in half, or if we could know that it is double the radius, which makes visual sense because in this image here, this is going to be the diameter. So all the way across the circle, making sure it's going through the center. So if you were measuring the circle's diameter, you'd make sure you're in the center. It's the longest distance across the circle. Those are probably going to be the two that we're most familiar with, but there are a bunch of other vocabulary words for circles. The next one is called a chord. A chord is a segment with 2 endpoints on the circle. So the diameter is a chord because a diameter has 2 endpoints on the end of the circle and goes across the circle. But also, this segment from E to C, it goes from the endpoints on the circle across the circle. Not through the center, because that would make it a diameter. But it is a chord starting and ending on the edge of the circle. That's a chord. The next vocabulary word is a secant. Say the word secant. Yeah, it's a weird word to say the first time you say it. A secant is a line or a segment that intersects the circle at 2 points, but also exists inside and outside the circle. So a chord stops on the end of the circles, but a secant line is a line that's going to extend forever and ever. So it's extending away. That is my secant. It has 2 endpoints on the circle. A tangent, A tangent line is going to be a line or a segment that touches the circle at exactly one place. Let's highlight the word one point. It is perpendicular. That's important to the radius at that point. So we're going to draw a couple things for the tangent line here. The tangent line is a line that just barely touches the circle at all. So in our image, that's going to be this line right here, bless you. Do you see how it comes in and just barely touches the circle at one point? That means that at that one point, it is perpendicular to the radius. Perpendicular means what kind of angle? How many? The degrees. It's a right angle. Sorry, I guess I should be more specific. How many degrees are in a perpendicular? 90 degrees. Very good. Okay, we need to know that. The next vocabulary word is point of tangency. Now this one, it kind of makes sense just by what its name is. Point of tangency means that it's going to be an exact point where the tangent line touches the circle. So our point of tangency, exactly where it touches the circle, is right here. Point B is the point of tangency. It's exactly where my yellow tangent line comes and touches the circle. Actually, while we're at it, why don't we add the words down here as well in the color if you have color code. So on the blue, or on the red, I'm gonna write radius. Write it underneath. Radius. And then we have our diameter. We have our chord. And we had our secant. Then we had our tangent line. And then we had our point of tangency. It's probably helpful to have those words down there. I know it's color-coded, but just in case you run out of colors here. The next vocabulary word is called a central angle. Central angle, the word central angle make me think of inside and angle, and that's exactly what it is. A central angle is going to be an angle whose vertex is on the center and whose sides are radii. Think of this as a pizza slice. So this angle right here, this little pizza slice of my circle, is called a central angle. As long as it meets at the center of the circle and then uses two radii to go to the outside, it is a central angle. And then last but not least, we have our intercepted arc. I'm not going to highlight the words intercepted arc. I'm going to come in here and I'm going to highlight the word minor arc. There are two types of minor arcs and a semicircle that have to do with the intercepted arc. An intercepted arc is like the pizza crust of your pizza slice. Your minor arc is going to be exactly that. Your minor arc is the small pizza crust from your pizza slice of your central angle. Minor means small, which obviously means major means big. So if we were doing a major arc, which I'm going to leave the same color but not highlight, I'm just going to do it in pen. That means all the way around here, this is my major arc. Because I have a small minor arc that's in my highlighter color. And then I have my major arc that's just written in pen. Minor means small, major means big. But y'all got that last time when we talked about major and minor diagonals. Semicircle, I think we know. A semicircle is an arc that is exactly 180 degrees. And it is named by 3 letters. So now that we have the image, bless you, color-coded, what we need to do is we need to actually name all of the items that we highlighted in the image. Okay, the naming of these pieces of the circle is important because you have to tell me specifically what kind of shape they are. Let me answer the phone real quick, hold on. Sorry about that, I'm back. All right, so again, naming all of these pieces is important because they're different types of objects in geometry. Some of them are lines, some of them are line segments, some of them are angles, some of them are, yep, that's about it. So we need to make sure that we label them correctly. So for the first thing, we're going to look for the radius. The color of my radius is red. Where does this radius start? Point A. Where does it end? Point B. So that is a line segment. So to talk about the radius, we're going to call it AB, but we're going to make sure we put the line segment symbol on top of it where it's just like a stick above A and B. For the diameter, I also only need 2 letters. I need where it starts and where it ends. Where does the diameter start? Point, which one? D, and where does it end? Point F. So that's a line segment since it starts and stops. There's no arrows. So I would call the diameter line segment DF. The chord is also a segment because it has a starting and a stopping point. So we're also going to call it a segment with the little line above it. The chord, which is dark green, where does it start? Point E, where does it end? Point C. So we will call that segment EC. The secant line, I gave you a hint with the word line. Since there are arrows at the end of that purple secant line, when we write this down, we're going to put the little arrows on top of those letters. But give me the 2 letters that create that line. Point E and D, you could say DE or ED, it doesn't really matter. But as long as you put the symbol for a line above it, which is with an arrow, not just a little line segment. Tangent line also gave you a hint that it has to be a line above it. I still need 2 letters to name a line. So I know that my point of tangency is here at B, but is there another coordinate point, or point, coordinate point is the wrong word, point on this yellow tangent line I can use? G. So I'm going to call the tangent line, line GB. Remember back to Unit 1 when we learned this, it doesn't matter if you say GB or BG, that's the same line. Ooh, and I already gave you this one. What is the point of tangency here? B. So you're going to say point B or letter B as long as you're indicating that it is point B. I like to put the little dot next to it so I know I'm talking about point B. Central angles. When we're describing an angle, we need the 3 letters that create the angle. So I have this pink central angle. What are the 3 letters in the correct order that create this angle? I want the 3 letters that help create this pink angle here. Okay, A, B, and F, yes, but we have to put them in order because if you say A, B, F, I go A, B, F. Is that where the actual angle symbol is? No, so what order should I say it? F-A-B, fabulous. I love it. Get it? Because it spells F-A-B. And since it's an angle, we put the angle symbol in front of it. Angle F-A-B. You definitely could have called that angle B-A-F. That's the same. As long as the A, the turning point, the elbow of the angle is in the center, you're good. Now, the arcs, we have not discussed the symbols for arcs yet, so you're going to learn them today. The minor arc or the smaller arc, I just need 2 letters. Where does the minor arc start and stop? What 2 letters? B and F. So when I write that down, I'm going to say B and F, but I put an arc above it. So it's a curved line to show that we're talking about the pizza crust. For an arc, the pizza crust. For a major arc and for a semicircle, you have to give me 3 letters so I know what direction around the circle you're going. So for this major arc, I need 3 letters. Where does it start? What does it go through on the inside? A whole bunch of things. Give me one of them. It doesn't really matter which one. D. And where does it end? B. So we can call this major arc FDB with the arc symbol above it. Now you could have picked any of those letters in between F and B around the large part of the pizza crust to call that major arc. Now for the semicircle we know is half of a circle. If I'm looking at the top half of this circle, what point starts the top half of the circle? D. And if I want to make it all the way to the other half of the circle, what point do I go through? E, and I end at. So for a semicircle, I also need 3 letters, D, E, and F. You could have said F, E, and D. That works as well. The order, as long as the one in the middle is in the middle, you're good to go. So we've got all of this vocabulary, and we're going to be discussing the different characteristics of this vocabulary for circles throughout the next few days of this unit. But I need us to really be able to identify these different parts of a circle. So to practice today, and so I can stop talking for a second so you don't have to listen to my horrible sounding voice, we're going to play a game kit for a while that's going to show you an image, and you're going to identify the vocabulary word. Oh, I forgot to pause this. The first part of a circle that we're going to explore more in depth is the tangent line. So remember, the tangent line was that line that just comes in and barely touches the circle. So we did that one in yellow if you're trying to keep the same color scheme. A line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So if we look at the image here, if we have this radius and a tangent line, I've drawn, you can't read that word perpendicular, can you? Let me write it in blacks just so it's easier to see. Perpendicular. It's perpendicular to the radius. Since it becomes perpendicular to the radius, do y'all see how there's a tiny little triangle that is formed between the radius, part of the tangent line, and this invisible line that I drew in with like a dashed mark? That means that we can prove that a right triangle is formed using Pythagorean theorem. What we're going to do is we're going to check to make sure that the hypotenuse squared is actually equal to the two legs of this tiny right triangle squared when you add them together. So if you look at example 2, I already worked that one, but I need you to highlight along with me so that you have some good notes here. Oh, that didn't stick. Here, I want you to highlight the tangent line in yellow if you're following along with my color scheme. The tangent line is this line right here. We're hoping that this tangent line is actually perpendicular to that tiny radius. We're going to highlight the radius in red. To check this, what we do is we take the hypotenuse, which is the longest side. My longest side is here. It says 37. That's the biggest number. And we're going to square 37 by itself. I get 1369. Then we're going to check and see if it's equal to those side lengths, the legs, squared and added together. So in my calculator, I did 35 squared plus 12 squared, and I got 1369. Are these the same number? Yes, which means this is a right angle, which means, yes, ST is actually tangent to circle P, because we actually proved that that right angle exists. You are going to do example 3. I'll help you by highlighting, but you're going to actually solve the question, which means you may need to go grab a calculator. For number 3, which of those side lengths, 24, 44, or 51, is the tangent line? Tangent line, remember, it means it touches the circle only in one point. My 44 is the tangent line. What is the radius? 24, which means what is my hypotenuse? 51. I want you to do like I did here for the math, and I want you to see if that hypotenuse squared is actually equal to the sum of the legs squared. If it is not equal, you're going to say no. It is not tangent. I'll give you some time to work. Just to keep going, because I see a lot of us are finished, what we should have done on this problem is we want to take the hypotenuse, which for us is 51, and we're going to check if 51 squared is actually equal to, because I don't know if it's equal to yet, the legs, which is your tangent segment, and your radius squared. Well, when you do this, 51 squared is 2,601, and 44 squared plus 24 squared, if you did that in a calculator, is 2,512. Are those equal? No. The 2601 is bigger, so that means that no, this is not a tangent line. We cannot put that little right angle thing here because it's not actually a right triangle. It would be an obtuse triangle, FYI.
So they have to equal the same thing, though, it's right?
Correct. If they equal the same thing, you say yes because it makes a right triangle, which means that it's tangent. Yes. For number 4 is a more difficult algebra question, but a really easy geometry question when you get down into it. I've done most of this problem for you, but you're going to help me finish. So we look at number 4. It says, in the diagram, point B is a point of tangency. If we look at point of tangency, that means that this is exactly where the tangent line intersects the circle. So we know that right there, since that's a point of tangency, we have a right triangle. It's telling us it's tangent. I don't have to figure out if it is. It's telling us it is. But it wants me to figure out the radius. It wants me to figure out this distance here. But here's the problem. They also said this is a radius right there, which means the entire distance of this hypotenuse is not just 50 feet, it's 50 plus the radius. So when I set up Pythagorean theorem here, my first step doesn't just say 50 squared, it says 50 plus r squared. That's my hypotenuse. Then I'm going to set it equal, I know it's equal, they're telling me it's tangent, equal to the legs, 80 squared plus r squared. Here's the algebra that you may have forgotten. In Algebra 1 and 2, if you've taken Algebra 2 so far, when you do 50 plus r squared, that means we're doing 50 plus r multiplied by 50 plus r. This is a double distribution problem, also known as FOIL. When you learn this in Algebra 1, you may have done this step in a box, like a Punnett square. For me, I'm not showing you the Punnett square, but I can if that sounds like something familiar. But what we're going to do is we're going to take this first number 50 and we're going to multiply it to both terms in the second parentheses. So 50 times 50 is 2,500. 50 times r is 50r. Do y'all see how my arrows did that? Then I move to the second number. R times 50 is 50r. And r times r is r squared. On this side, all I did was do 80 squared, and then I just dropped it down a few times. So mathematically, all I've done so far is I've expanded that binomial and then multiplied 80 times 80. I need to solve for the radius. I need to solve for r. What do you notice is positive on both sides of the equation? R squared. If you have a positive r squared on one side and a positive r squared on the other, they can cancel each other out. This is not the case if one's positive and one's negative, but if they're both the same sign, what you can do is you can cross them out. For problems like this, you should be able to cross these out. If you don't, you might have done something wrong algebraically. But from here, we would just use the box method. Once the r squareds are gone, you can use the box method. I am going to solve this one using inverse operations, but if you just write a note for yourself that you can box method, that's fine as well. Inverse operations wise, I'm going to add together the 50r and the 50r. What's 50 plus 50? 100. So I have 2,500 plus 100r equal to 6,400. Again, you could use box method if you're already like, I would prefer box method. The moment you cross out those r squares, it's a box method question. I'm going to subtract 2,500 from both sides so that the r term is by itself. That means this becomes 100r equal to 3,900. What's this last step to solve for r? Yeah, divide by 100 on both sides. Which if I'm doing this in my head, so you don't have to do it in a calculator, when you're dividing by multiples of 10, the zeros cancel each other out. So what is 3,900 divided by 100? 39. So the radius here is 39 units long, which is what it asked me for. So again, this problem at the very beginning is a little bit complicated because of this double distribution. However, once we start solving, the r squareds cancel out, so it's actually a box method question. So trust the process, follow your arrows, all of that good stuff. I am going to ask you to do a problem like this on your levels and on your homework. Does anyone have a question before we leave this problem? Okay, the last theorem for today is a really, really easy theorem. It's called the external tangent congruence theorem, but that's a lot of words. I'm going to call it the snow cone theorem. Why do you think I call this picture the snow cone theorem? It straight up looks like a snow cone to me. In your snow cone, if you were to actually get a snow cone or an ice cream cone, I guess, you want the cone part to be real sturdy. You don't want your ice cream or your snow cone to fall out. So to make it sturdy, we need both sides of my cone to be the same. And that's what the external tangent congruence theorem does. It says if SR and ST are tangent lines, then they are congruent. Notice that we have the little marking there to show that they are congruent. What does congruent mean? Equal. So we are going to be able to set the sides of my snow cone equal to each other and be able to solve more complicated problems. Again, this is only for tangent snow cone lines, not for secant snow cone lines or anything, just the ones that actually make it look like a snow cone. In number 5, it says RS is tangent to circle P, C at point, bless you, point S, and RT is tangent to circle C at point T. So we are saying officially that RS is a tangent line and RT is a tangent line. If they're both tangent lines, then they are equal to each other. So we can put the little tick marks to show that they're equal. Mathematically, since they are equal, what we're going to do is we're going to say 3x plus 4 has to be equal to 28. Absolutely, yes. You are solving this either with inverse operations or the box method, because once you have an algebraic linear equation set up, no squares or anything, you can definitely use the box method. And I'll give you a second to finish this one. I want to see if you can figure out the value of x, which is what this question is asking for. Since I used inverse operations above this, I'll show the box method, but you can use whichever method you like. There is one term here with an x and 2 terms that are straight up by themselves. So here's what your box should look like. We drag and drop the 3x. We drag and drop the 4. Oop, change the sign. We drag and drop the 28. Drop down to 3x because it doesn't combine with anything. Negative 4 plus 28 is positive 24. And what do I divide by? Divide by 3, so that means x is equal to 8. Is that what you guys got? Amazing. Fabulous. Bonus question here. And don't think too hard about it because it's a really obvious answer. How long is RT?
8? No.
28. There's 2 ways you can figure this out. You could take the number 8 and plug it in. 3 times 8 is 24, plus 4 is 28, or just straight up remember, these have to be the same. So if RS is 28, RT is 28. In case it asks you a further question, make your life easy. The last part here, number 6, I know I've already worked to the whole thing, but I wanted you to see just a little bit more complicated math that you could possibly have to do. It's the same kind of problem because it says M and N are points of tangency, which means that these little sections right here are tangent lines. Snow cone theorem means that they're the same. In fact, they're the same because if you draw on the radiuses, do you notice that that is a kite? And when we studied kites in our last unit, we noticed that the consecutive sides are congruent. So the radiuses are the same and the sides of my snow cone are the same. So this follows from the properties we learned in chapter 7 with polygons. So mathematically, to solve this one, I would just say x squared would have to be equal to 9. And so we do x squared equal to 9. Did y'all remember that the inverse of squaring is square rooting? But when you physically put a square root into a problem, when you take a square root, you have to include this plus or minus in front of it, which means there are 2 answers here. The square root of 9 is 3. But we're going to answer with both positive 3 and negative 3. There were 2 answers for x there. That's just a nice little algebra review for you. Those of you who have taken Algebra 2, that should be more familiar. Those of you who have only taken Algebra 1, maybe not as familiar for you. Okay, so we have our vocabulary for the circles. We have our deciding if it's tangent using Pythagorean theorem, and we have our snow cone theorem. Those are the 3 things we learned today, and those are the things you're going to practice in your levels today.